in measuring the growth rate of an algorithm. Now, from this lecture onwards, we will dive deeper into the concepts of Big O notation. In this lecture, I will introduce the Big O notation, and in the subsequent lectures, we will learn a lot about Big O notation. Let's get started with this lecture and let's see what are the topics. The topic of this lecture is the Big O notation. In this lecture, I will introduce the Big O notation, so let's get started. So what is the Big O notation? Big O notation is the way to describe the performance of an algorithm with respect to the input size. This means Big O notation tells how fast an algorithm is or how much memory space it takes with respect to the input size. The performance of an algorithm means how fast an algorithm is or how much time it takes to execute and how much memory space it takes to execute. So performance is measured in two terms. One is time and the other one is memory space. Although throughout this course we will focus mostly on the time factor. The performance is measured based on time. But sometimes we will also mention the memory space, but mostly time is the important factor. So with Big O notation, we describe how fast an algorithm is with respect to the input size most of the times. Also, in one of our lectures, we discussed linear search and binary search. We learned that in case of linear search, the number of comparisons is directly proportional to the input size. Now, what does this mean? In order to understand this, let's compare the number of items with the number of comparisons a linear search takes. So, let's compare the number of items with the number of comparisons. Number of items means the input size. Let's say that the input size is 10. How many comparisons do linear search need? It needs 10 comparisons. It needs 10 comparisons to come to the conclusion whether the item we are looking for is available in the list or not. Similarly, if we have 100 items, then linear search takes 100 comparisons. If there are 1 million items, then linear search needs 1 million comparisons. Clearly, from this data, we can deduce that if there are n items, then there will be n comparisons. So the relation between the number of items, that is the input size, and the number of comparisons is directly proportional relation. This means number of items is directly proportional to the number of comparisons. And this means the running time of linear search is Big O of n. Now what does this mean? Here, we are using Big O notation to describe the performance of linear search with respect to the input size. As the input size grows, linear search grows linearly. This means as the input size increases, the number of operations or the number of comparisons also grows linearly. Or in other words, it increases with the same rate as the input size. This is the meaning of linear growth. So growth rate of linear search is linear. This means as the input size grows, the number of comparisons or the number of operations also grows with the same rate. I hope this idea is clear. So, with Big O notation, we are describing the performance of an algorithm or how fast an algorithm is with respect to the input size. As the input size is n, number of comparisons is also n, and that's what we have mentioned here. This represents the number of comparisons or the number of operations linear search took. So that's the running time. Now let's visualize the running time through the graph. This is how we can visualize the running time. We took this table of the number of items and the number of comparisons, and by using this table, I have plotted this graph. The x-axis represents the number of items, and the y-axis represents the number of comparisons. If there are 10 items, then there are 10 comparisons. If there are 100 items, there are 100 comparisons. If there are 1 million items, then there are 1 million comparisons. This is what we can observe. If there are 1 billion items, then there will be 1 billion comparisons. This is what we can see here. So the growth rate is linear. This means as the size of the input increases, the number of operations increases with the same rate. This is linear growth. I hope the concept is now completely clear. But why I haven't mentioned time in seconds? Here I have written running time is big O of n, which means the growth rate is linear. But I haven't mentioned the time in seconds. The reason is pretty simple. The big O notation does not tell speed in seconds. It helps in comparing the number of operations. So it tells the number of operations, not the speed in seconds. So the speed of an algorithm is determined through the number of operations. So in big O of n, n represents the number of operations. This is not the exact time. That is why we never mention the speed in seconds when we describe the running time with big O notation. So big O notation does not tell speed in seconds. It does not give us the exact running time, but it tells the running time through number of operations. I hope this idea is completely clear. So with this we understood what is big O notation. Now we are done with this lecture. Okay friends, this is it for now. Thank you for watching this presentation.